So talking of team, the whole team's here. A slight change of plan. I'm not Amanda, but I'll be giving the first half of the talk, and then Josh is going to take the second. We'll get into more of the details of printing. Okay, so start with the question, what if solar cells were everywhere? So familiar with solar cells, usually you find them on rooftops, big solar farms in fields, but we thought, what if we can take that and bring it into our lives, integrate it into everything we do? So our lives are becoming more technology-driven, with smartwatches, sensors everywhere. All these things need power, but to get that power is, we need batteries and things like that, but it wouldn't be great, the solar energy all over the place, if we could use that at the point that it's required. So that's what we're going to try and do. So this is our project here, Solar Skin. So additive manufacturing, customized, fully integrated photovoltaic products. So we're going to use additive manufacturing to take these solar cells, which are usually big, industrial, large-scale, bulky products, and get them smaller, integrated into manufacturing lines. So this is how we're going to do it. So we're using an iterative plan here. We formulate the ink, we make the material, we test it, and then we also use the tests to feed back and improve our formulation. So just to start, we're not going into too many details, but I couldn't have a presentation without having this diagram at least. But perovskites, for those that don't know, just a chemical of this crystal structure here. But what you need to take away from this is that they are solution processable photovoltaics, okay? And they are taking the photovoltaic world by storm lately. But we're not really interested in their high efficiency. What we're interested in more is their customizability, okay? So general formula is AVX3, but we can swap in and out various components for these positions and change the properties of the material. So as an example here, if we change the X from bromine to iodine, in different mixtures, you can see how the color changes from yellow through reds, browns, and blacks. So that is changing the band gap, that's changing the amount of light that is absorbed, like the position of the solar spectrum that it's absorbing. And so we can use that to tune our absorption for the environment where we're going to find the solar cell in. So the color is great for aesthetics, if you want to have a nice red solar cell on your nice red bag or whatever. But also this is functionality, like I was saying. We can tune our solar cells to the environment that we find the solar cells in. And we use that then in these models. So I'm not going to go into huge detail here. If you want to find more, speak to Abhinav with his excellent poster downstairs later. But just briefly, this is an example of one of the things we can do. So this is using an optical model to calculate the amount of light that's absorbed in the absorber, and therefore generating current. And we can work out what thickness of that absorber we'll need, given the environment and all the other layers, to make a good solar cell. So we can then feed that back in to change our thicknesses and to optimize our design. We're also using inkjet, which is a highly customizable fabrication process. So we can make any pattern we like. So obviously we had to do the logo. And Abhinav's done this wonderful image as well. Obviously, this isn't making the best use of the area if we want the most efficient solar cell, but perhaps there's a use case out there for beautiful solar cells, who knows. But also it allows us to print on flexible. And also we can use these patterns then to integrate however we like on a product surface. So if there's other elements on there we need to print around or things like that, we can do it with inkjet. Okay, so the ultimate plan is to create two different prototypes to demonstrate the wide range of possibilities with this technique. So we've got satellites, which we heard from yesterday, using mylar sheets, so very, very flexible material, print on that, send up into space where the solar spectrum is very different to what we have on Earth. And then flexible devices, so that's using PET, a bit more robust but still flexible material for smartwatches and that kind of thing. So to tell you more about the details, I'm going to hand over now to Josh. take us into the printing.
This will be a smooth transition. I'll probably just hold this, I suppose. So here we see the inkjet printer. I'll just say thank you to Kate for letting us use her inkjet printer, and she was my PhD supervisor, so no pressure for this talk now. But yeah, so I'm the kind of technical lead on the fabrication side of this, so the inkjet printing primarily. You can kind of see here a few technical details: stationary print head, the stage is moving around. It's a 50 micron piezoelectric drop-on-demand head for anyone who likes the technical side of things. So most of my work is actually primarily focused, or is really starting to focus now, on reducing the toxicity of the solvents, and also looking at more green, just generally safe, better solvents for the users. Anyone who's actually going to use these in industry, they kind of need to be safe. They're not going to be sealed away in a glove box. A lot of people might not have had the safety training that's necessary, so it's a really big, important thing. But in addition to being green and sustainable and non-toxic, we do need to end up with a printable ink, otherwise the whole thing kind of falls over. So that's what we're really working on. Cool, is this? Yes. So just a brief overview of a bunch of the different solvents that we've kind of had a look at. Obviously, it needs to be printable, but also non-toxic and green. So some of the solvents that we've looked at, GVL, DMSO, DEF, these are all solvents that we're taking forward and using as carriers for our ink formulations. Another sort of sneak peek, if you will, on some future work is ionic liquids. So these are incredibly interesting because they're salts, but they are actually liquid at room temperature, and that gives them quite a few very unique properties. And the two that we've looked at is methyl ammonium formate and methyl ammonium acetate. There's a few reasons for that. I won't go into that now, but basically they're the two promising ones that we've looked into. And the interesting bit is not only can these dissolve our ink precursors, they can passivate the deposited film, which is a really important thing. We need our solar cells to last. If we can avoid encapsulating them, that's another step in the process that we can remove, and it's less material use, so less material wastage. And just a little bit of technical data. So on the left there, we've got an X-ray diffraction trace. Basically, all this is telling us is we're depositing what we wanted to deposit, so that's great news. C, you can kind of just see this is imaging of an inkjet nozzle. And we've got a droplet diameter there that's probably around 50, 60 microns, because we're using this 50 micron orifice printer head. And then we've got a nice little print down there of the chemical formula of perovskite, because that's something that you like to do. So we do actually have some samples here if anyone wants to come and have a look at them, or we can pass them around in a minute. Benefits of having this conference on your home turf. And then again, just a few printed prototypes. So some of these we've got here with us, like the Fitbit strap that's got the Connected Everything logo on. So that's some integrated perovskite. It's obviously not a full cell, but it's a proof of concept. You can see, so quite a lot of these are actually on flexible substrates as well. So this is kind of groundbreaking stuff for a lot of the photovoltaics. So yeah, thank you, everybody. You can see the three of us along with Abhinav here. Yeah. Any questions or anything else?